everyone. My name is Christian Checo. Today I'm joined by Aziz Almosa, Peter Campolone, Michael Tyler, and Cooper Hobbs, and we are Team Infineon. This year we were tasked with creating a Generation 2 SPEC tester, which stands for System Power Extended Cycling System. The motivation for this project was to improve upon Infineon's current DC-DC buck converter testing system. Now, a buck or step converter is used to take supply voltage and drop down to a lower desired regulated voltage. These types of regulators are known as switch mode regulators, and they utilize pulse width modulation. Basically, they consist of a power phase and a power phase controller. The controller modulates a signal to the high and low side MOSFET to generate a square wave at the switching node here. This square wave has the amplitude of the supply voltage and a carefully controlled duty cycle. Now, this pulse width modulated signal is essentially averaged by an LC low-pass filter at the output. This generates a simple steady-state equation where the output voltage is equal to the duty cycle times the supply voltage. For example, a 20% duty cycle and a 10-volt supply voltage, there's a 2-volt regulated output. Now, things are a little bit more complicated when transients in current demand are seen, as the phase controller must be able to accurately modulate the duty cycle and able to maintain a constant output voltage. As you can see here in the diagram, when a step in the load current requirements is seen, the capacitance at the output node is drained, resulting in a drop in voltage. The phase controller detects this change and it increases the duty cycle in order to slowly increase the supply of current. Eventually, it goes actually past the load requirements to recharge the load capacitance and restore the output voltage. When the phase controller detects this, it will then return to steady state, providing exactly the load requirement and return it to a steady state duty cycle. I will pass it over to, now a testing platform must be able to accurately push these devices through a large range of stress in order to accurately test them, all while collecting data. And this sort of large-scale testing platform would allow Infineon to compare configurations and performances across many devices, and allow them to be innovative and develop in a competitive industry. Aziz will tell you about our current project outcome.
So the best estimated outcome for this project was to create a system capable of the telemetry and data consolidation for one entire neighborhood, which is 10 devices. And from there, we had planned to expand our design and work with all 60 devices. Although, despite these ambitious goals, we were not able to achieve the best estimated outcome. During the last semester, we met a significant number of setbacks that limited the available time for us to complete this project. However, despite this, we believe that we laid a solid foundation for the next team to build upon and utilize in the SPEC platform. And now I'll pass it out to Peter.
Thank you, Aziz. So, in terms of hardware accomplishments, we're going to start with a block diagram converter system. All starts FPGA, a Cyclone 5 Intel FPGA. From there, we wrote a I2C controller using VHDL, which allows us to communicate with Infineon SPEC tester to receive things primary, like telemetry data, voltages, currents, power, things like that. That's the primary focus of that. And it also will later be used to get fault data. From there, we designed a waveform generator board, which we'll talk about a little later, and that is communicated to the FPGA using a SPI controller. We also wrote that in VHDL, and we'll talk about a little bit. And then our software computer engineers created a PC GUI, which allows a way to communicate with the FPGA and the SPEC tester, so we have the whole communication path covered. All right, so first, I2C controller, completely written in VHDL from the ground up. And like I said, current functionality is telemetry, voltages, power, and current. That's the main focus right now. And eventually, like I said, used for fault data, fault statistics, fault management. So you can see here just an initial test of it, a little oscilloscope capture showing the data address, device address for the write bit, and the data address, or the register address for the specific telemetry value. Then we get to the waveform generator board. Hardware team, we designed this because we saw that we found a a more advanced stack that we could use on the spec tester. And the primary reason for this is that it has built-in SRAM. It allows us to store waveforms. We can customize those. We can specify a few things to those. Send those to here from the FPGA, and then we can use that for sending current transients to the spec tester. And the good thing about it, we designed it so it plugs right into the bank of our FPGA when the GPIO connection plugs right on. Like I said, communicates over the spec bus. So, just a few schematics so you can get an idea of how it works. Primary IC on here, 12-bit quad DAC. Quad means 4 individual DACs on one board. And primary, value to it is the integrated SRAM. From here, it needs a clock signal, so we have a differential clock generation chip right here, and all the associated components to make that work. And lastly, a differential output receiver, this IC here, used for current voltage conversion and gain modification. And then the SPEC is also written VHDL from the ground up. And primary focus right now, sole focus, communicate with the DAC and the waveform generator board to provide specifics about the current transients. And you can see a model sim simulation. You can see sending the configuration data. These are all 32-bit values. You can see there are 6 of them. And all the VHDL code is based around a finite state machine. That will define how to write this configuration data. And by modifying a few things, we can change what that configuration data is. And lastly, in terms of hardware, that SRAM will store up to 4,096 data points, which is more than enough for what we need. Like I said, waveform generation done exclusively within an FSM and the VHDL code. The primary configurable values are rise time, fall time, and high time, which is otherwise known as duty cycle. So with that, I'm going to hand off the mic, and he's going to talk about our software accomplishments.
Okay. So, as Pete was mentioning earlier, that the software team was responsible for creating the user interface. To do that, we used a program called Qt, which is specifically used for graphic user interfaces. It's easy to use, drag and drop, and it has the ability to cross-platform, and it uses C++ backend programming. And to interface with that FPGA board, we decided to use Python, because it has a UART protocol that has the ability to communicate with the FPGA board, and it also has the ability to store data in an Excel file. So as you can see here, this is our simple user interface. It's made up of 60 single device icons, which is this single fan picture, 6 neighborhood controls, which is 2 of these icons overlapped, and a master control, which controls all 60 devices at the top center. So first off, I'll go over the interface with the master control and the neighborhood controls. So once a user clicks on one of these icons, a box opens where a user would click on one of these checkboxes, which would be reserved for hardware tests. And once the user hits OK, that the commands are sent over to a text file, and then the Python code reads that text file to send to the FPGA board to test the hardware. Now for the single device control, a user would click on an icon, and this box appears on the right side of the interface. At the top right is where the data is shown for voltage, current, power, and then the user would also have the ability to control one device by clicking on the hardware control, which then has the checkboxes appear in the same interface as the neighborhood and master control. They click on the checkbox and hit OK, and then those commands are sent to a text file, which is then read by Python and then sent to the FPGA board.
So because we were ultimately unable to communicate with the FPGA, to test our GUI, we developed a Python program to simulate the expected values we would get from the FPGA. This program generates the values for current, power, voltage, etc., and outputs those values into a text document. From there, the GUI is able to read this document, parse the data within, and display it to the end user accordingly. And the GUI is also able to export the data into an Excel file, which will in the future aid the construction of a database for the next team. And finally, we'd like to acknowledge our technical directors, Martin Rodriguez and Gerald Gallipo, as well as Dennis Gallipo and Dan Clavette for their support in our endeavors. And in addition, Dr. Sunak, without whom none of this would be possible.